Students, in this short video, we'll be going over some review problems for the final exam. So the first problem we're looking at is to talk about some figures that have half-turn symmetry and some figures that do not have half-turn symmetry. So we'll go into GeoGebra to investigate this. So the first figure that someone suggested was a square. Does a square have half-turn symmetry? So we'll start by making a square using the regular polygon tool. You tap twice and tell it 4 vertices. So there's our square. Now we'll rotate this 180 degrees to see if it has half-turn symmetry. First of all, to find the center of rotation, I'm going to put on diagonals and make the intersection of my diagonals the center of rotation. So we'll rotate about a point. We'll highlight the square with the center. We'll tell it to rotate 180 degrees. And there we see it landed right on top of itself. So this square does have half-turn symmetry. All right. Someone also suggested an equilateral triangle. So let's investigate that. So again, we'll use our regular polygon tool. This time we'll tell it to put on 3 vertices. And I'll put a point at the center of the equilateral triangle to use as the center of rotation. Just eyeballing this here. And now we'll rotate this equilateral triangle around that point by 180 degrees. And we see that the equilateral triangle does not land on top of itself when we rotate 180 degrees, so it does not have half-turn symmetry. That does not mean, however, that it has no rotational symmetry. It's just not 180-degree rotational symmetry. So let's look at what rotational symmetry this equilateral triangle would actually have. What I'm going to do is put on segments from this center point to each vertex so that you can visualize these central angles here. And all the way around a point is 360 degrees, and we've got 3 equal central angles. So if we take 360 degrees divided by 3, that will give us the turn symmetry for this equilateral triangle. So 120 degrees is going to be our smallest angle of rotation. And if we rotate it, it will land on top of itself. So let's just test this. And of course, you can go up by 120. So you could rotate 240 degrees, 360 degrees, all of those. We can keep adding 120s. It will continue rotating and landing on its footprint. Okay, let's go ahead and rotate around the point and highlight the triangle. Highlight our center of rotation, and this time we'll tell it 120 degrees. And we'll go clockwise, counterclockwise, that'd be great. And then you can see it landed right on top of itself. Okay, you could look at some other shapes as well. Let's look at a regular pentagon. We'll tell it 5 sides. We'll put on a center of rotation. And then we can rotate the pentagon around the point 180 degrees to see if it has half turn symmetry, and we see that it does not. It's not land on itself. But instead of trying something with an odd number of sides, we could try a regular figure with a regular polygon with an even number of sides. So why don't we try the regular hexagon? We put on the center of rotation. We highlight the hexagon. Highlight our center of rotation, tell it 180 degrees. And then we see it landed on top of its footprint. So a regular hexagon would have 180-degree rotational symmetry. In other words, half-turn symmetry. A regular octagon would as well. All right, if you wanted to find more of the central angles, you could continue using this formula here. 360 divided by the number of sides gives you the turn symmetry for that figure. So a triangle has 3 sides. So 360 divided by 3 gives us 120-degree turn symmetry. On the hexagon, it has 6 sides. It's a regular hexagon. So we can take 360 divided by 6. And that would give us this 60-degree turn symmetry. So 60 degrees would be our smallest angle of rotation, and then we could continue adding 60. So 120 works, 180, we can continue on. If you had a regular end gun, you could just take 360 divided by 8. Okay, now the last problem that we'll look at today is a question: if you have side lengths of 10, 40, and 50, will this make a triangle? So let's just check using the triangle inequality if we actually have a triangle here. So we'll call that one 40, we'll call that one 10, and we'll call this one 50. 50 plus 40 is greater than 10, so no problems there. 50 plus 10 is greater than 40, no problems there. However, 40 plus 10 is not greater than 50. It's exactly equal to 50. So what we would have here, if we just rotated this 40 to 40 unit side down, we would have just a straight line, and there would be no interior of the triangle. So we would say no, 40, 10, and 50 do not make a triangle.